Austrian skydiver Felix Baumgartner made it appear as though a bold jump is all it takes to return to Earth from the edge of space. However, the truth is that he wasn't truly in space, not just yet. Coming back from a higher altitude involves much more complexity than a glorious descent. The most perilous phase of a modern astronaut's voyage involves numerous critical steps that are essential for a safe return home. Therefore, let's explore in detail the precise process an astronaut undergoes to make their way back to Earth from outer space. Each return trip home is determined by first knowing the best course and steps for an optimal return trajectory. Earth constantly rotates and every other orbiting body has its own motion relative to it. To give you an idea on how this is generally done, if a space capsule is scheduled to return home to Earth from the ISS, experts on the ground need to prepare beforehand by taking into account the current orbit of the station, its speed, and the current orientation of the planet. They then calculate the capsule's trajectory that will enable it to land within the target destination and re-enter the Earth's atmosphere without burning up or bouncing off. Once the location has been determined, survey teams are then dispatched that will scout the actual validity of the area. The team needs to observe whether the location is flat or calm enough for a safe landing, or if there will be meteorological complications that might hamper the return trip. Once the course and trajectory has been determined, all on-board systems are given one last round of checking and testing. In the event of a certain malfunction, the course will be adjusted to compensate for time required to resume the return trip. Remember, the re-entry window doesn't just involve place, but also time as the Earth spins and as the vehicle orbits. With that, the time required to test the systems itself and any subsequent related actions will also be taken into account. The next step is to orient the vehicle into its trans-Earth injection window. For vehicles docked onto a space station or shuttle like the Soyuz or Dragon capsule, proper undoing procedures are carried out first. Separation is then usually done manually by pushing the capsule into a higher orbit, creating a speed gap between the station and vehicle so that they don't collide at the point where their orbits intersect. For vehicles non-docked connected to another vehicle or stationary body, such as an Apollo capsule, the procedure typically skips to directional orientation and the jettison of non-essential components. The remaining portion of the vehicle will then perform a course correction burn. The thrusters are fired to orient the vehicle towards its re-entry angle. This is a delicate step to ensure that the heat-shielded part of the returning module faces the Earth's atmosphere. Most heat shields are usually placed at the underside of the returning module, so it should be the side facing the atmosphere as it falls down where the whole module and the astronauts inside it will disintegrate. Then the vehicle performs a deorbit burn, a procedure that further decreases the speed of the vehicle in order to break its orbit enough for the atmosphere itself to act as a brake. The deorbit burn's duration depends on preliminary calculations, though it typically lasts more than 4 minutes. The deorbit burn is usually set at a curved angular path that both reduces re-entry speed and allows penetration through the atmosphere too steep, and the vehicle turns into a fireball and/or exerts too many Gs on the astronauts inside that they won't survive. Too shallow in the spacecraft bounces off like a rock skipping onto water. Exactly the angle you need depends on the shape and size of the craft, but generally it's about 40 degrees. A streamlined craft can more easily penetrate at a shallow angle, but a blunt shape can survive the heat more easily. Just before re-entering the Earth's atmosphere, often after the deorbit burn procedure, any final few non-essential components are separated using impact, less separation. Only the descent module will make it back to Earth as the others will burn up in the atmosphere. Once the vehicle has made contact with the Earth's atmosphere, it begins experiencing further deceleration, thanks in part to the dense air pushing onto the crack. This is also where the vehicle starts to heat up due to the massive friction and experiences as it pushes through the atmospheric layers. In fact, it gets so hot that the air around the craft is literally ionized into plasma, the glowing gaseous stuff of stars. This produces another side effect because of the surrounding charged particles. Ionization blackout occurs. This means electromagnetic signals get disrupted and communication with the spacecraft becomes impossible, at least until it gets further down and slows enough for the surrounding plasma to eventually dissipate. One important thing to note during atmospheric entry is trajectory maintenance. Though already calculated during the preparation phase, tiny adjustments in position and direction are often made as the vehicle falls further into the atmosphere. This is mainly due to the differing densities, speeds, and directions of wind hitting the vehicle. It can do this by rotating as rotating in one direction increases lift on the capsule, while rotating in the opposite way decreases lift. Without these tiny adjustments, the vehicle could dangerously veer off course, potentially moving significantly far off from the intended landing destination. During atmosphere entry, all vehicles typically start at almost 30,000 kilometers an hour. That's more than 20 times the speed of sound. After about 8 minutes of descent, the atmosphere will be able to decelerate the vehicle to just about 1,000 kilometers an hour. This is still way too fast for a gentle touchdown, though. So a series of parachutes are deployed. The first parachute usually provides preliminary deceleration, with the main parachutes deploying later to ease the capsule all the way towards touchdown. The capsule was suspended below the parachute at a specific angle relative to the ground to help dissipate heat gain through its re-entry. With a controlled descent, returning spacecrafts are usually able to minimize the G-forces experienced by the astronauts as much as possible, usually to around 4 gs, which is a relatively smooth ride compared to the 6 gs they experienced during liftoff. However, emergency re-entry procedures may force them to experience much higher gs. This was the case during the re-entry of the Suez TMA-10 in 2007, as it was forced into an unexpected ballistic descent of almost 9 gs. After its equipment was damaged, miraculously, all astronauts survive. The final stages of the operation occur when the vehicle is only about 5 kilometers above ground. The somewhat cooled down, but still very hot heat shield is finally jettisoned away. At this point, the initial parachutes have been jettisoned and the main parachutes have been working for several minutes, but an extra set of retro-rockets positioned below the spacecraft behind the heat shield prepare for firing in order to further decrease the speed of the vehicle as needed. The vehicle then internally adjusts to orient the astronauts upward to reduce the impact, as the crew seats have shock absorbers. Then, just as it reaches approximately a meter off the ground, the rockets fire in order to slow the capsule down to around 5 kilometers per hour. Though the capsule keeps moving downwards, the crew seats are cushioned by their shock absorbers. Outside the vehicle, flotation mechanisms may be deployed shortly before the last few seconds to help the vehicle stay afloat and upright in the event of a splashdown, but other more sophisticated landing procedures like propulsive landings are being developed as a third final touchdown method. Particularly for SpaceX's Dragon 2 capsule, think of those rocket sci-fi films landing down on alien planets. Basically, the boosters would not just act as minor retro-rockets, but will be ignited and used from a significantly higher altitude all the way down to its target location. Though some plans were scrapped in June last year, it remains as an alternative method of providing deceleration for the Amen spacecraft's final descent in the future, and that is generally how we get astronauts home today from space. However, several of these steps may differ depending on the vehicle used and the profile of the mission. This is especially true when the configurations of such vehicles are significantly different from what would typically be considered the bread-and-butter capsule or module type. The most common example is the standard space shuttle orientation in deorbit procedures aside. The space shuttle's plane-like form factor lets it use a combination of standard deceleration procedures and aircraft maneuver in order to land. After a deorbit burn, it falls down on its underside and then flies like an ordinary airplane until it reaches the runway where it lands. Parachutes then help it further decelerate. Another special case is the Dragon 2 capsule. As mentioned briefly earlier, it's designed to use an active powered landing system via boosters, completely ditching the use of parachutes during its lower atmospheric descent. This was initially due to the fact that it's designed to land, not just on Earth, but on destinations where parachutes may be ineffective, such as the thin and non existent atmospheres of Mars and our moon, respectively. Another special mention when it comes to landing spacecraft is Spaceship One and its current version, Spaceship Two. Technically, this spaceplane isn't capable of orbital distances similar to that of other manned capsules. However, it does demonstrate its feathered landing procedure, a method of controlled descent by tilting the wings down during free fall, slowing down the craft enough to not require heat shielding, much like a shuttlecock. This method is optimal for the craft due to its lower re-entry speed and lower altitude, though it's also only effective for similar suborbital jump shot launches. Developing these techniques to get our astronauts back home safely has cost the world's space programs billions, but it continues to be one of the most challenging parts of any trip to space. Do you think you'd have the physical and mental ability to land a spacecraft like this? Let me know in the comments down below, and thanks for watching.